Try to think of something where if you could test it, most people would have roughly the same score, and some people would have a really high score or a really low score. A good example of this is a measurement of someone's height. Think about it. Most fully grown teenagers and adults are roughly the same height. Sure, you'll get some dwarfs and giants, but we all have an idea of a normal height range. If we measured people's heights, say hundreds or even thousands of times, what we are going to discover is that a lot of people have a similar height and only a few people are really tall or really short. This is where the language comes from, having a normal height. If you do enough of these, placing the results on a graph, what we discover is something called a normal distribution. These types of graphs are called probability density functions, where the area is representative of the population. Interestingly enough, normal distributions arise in many human traits, not just the typical example of height or IQ. Let me introduce the personality trait extraversion. It is defined as a measure of interest and joy in social interactions, and is one of the dimensions of the Big Five personality model. You can measure this trait by asking participants to rate themselves on a 1 to 7 point scale, where 7 is strongly agree and 1 is strongly disagree, on items such as, I feel like I talk a lot, or I'm outgoing and I like to be with people. We may ask, say, 5 of these questions and sum the scores from the items, where the scores will range between 7 and 35. A person who scores 35 would be described as extremely extroverted, and a person who scores 7 would be described as extremely introverted. If we were to administer this survey to hundreds of people, we would see the same normal distribution display. Most people have roughly the same score, and a few people go to the tail ends of the distribution. Have a think about where you might sit on this distribution. You see, this will occur when investigating particular things. Most people are the same, and a small minority are different. This forms what is called a bell curve, or a normal distribution. Now, to get mathematically technical, a normal distribution is a probability density function where the area under the curve is equal to 1. The thing with normal distributions is that the area is perfectly symmetrical about the mean. The spread of the distributions is measured by a thing called standard deviations, or better thought of as deviations from the standard, that is, the mean. 68% of the population lie within 1 standard deviation of the mean. 95% of the population lies within 2 standard deviations of the mean. And if you lie outside of 2 standard deviations, you are considered to be on the not normal ends of the distribution. And going 3 standard deviations out from the mean, that contains 99.7% of the population. And if you lie in this section, you are considered to be on the extreme end of the distribution. To help interpret normal distributions, there is a thing called z-scores, where you take your score, subtract it from the mean, and divide it by the standard deviation. Really, it's just a score that tells you how many standard deviations you are from the mean. Let's do an example. Say we have a normal distribution representative of some exam where the mean is 10 and the standard deviation is 3. If I score a 14.5, calculating the z-score will give me an indication on where I fit in the distribution. If I evaluate this calculation, I get a z-score of 1.5, or in other words, I am 1.5 standard deviations above the average. However, if I did the same mini exam and the mean is 11 and the standard deviation in this case is 1.5 and I score a 14, I calculate the z-score and what I find is I get a z-score of 2, or in other words, I'm 2 standard deviations above the average. Reflecting on the two cases, it would be better to score a 14 on the mini exam than a 14.5, because the normal distribution provides the grounds for comparing your results in contrast to the normal, rather than just the result itself. Your result is better if you're further away from the mean, not just if you get a high score, and this is displayed by the z-score. You see, this is the nice thing with normal distributions. It creates a measure of individual scores and where they sit on a population scale.